Hi everyone, welcome to the workshop 2 of IEEE Industrial Electronics Society Generative AI Challenge 2025. So today we have Vidura Sumanasena, our guest speaker, with us to talk about um, on the topic of a deep dive into large language models, breaking down the tech that powers artificial intelligence. Vidura is a doctoral research at Center for Data Analytics CDAC lab at La Trobe Business Schools at La Trobe University. And without further ado, let me hand the screen over to Vidura. Vidura, over to you.
Thanks, Isuru, for organizing this event. And let me share the screen. So good evening, everyone, and maybe good morning as well for some. Hope you can see the screen. And hope I'm audible as well. Let me remove this. All right. So today's session, we will talk a bit about large language models and how the internals of large language models work. So I'm Vidura Sumanasena. I'm a PhD candidate at Center for Data Analytics and Cognition. So my primary research area is basically neurosymbolic AI. And I also look at how large language models and neurosymbolic AI, like vector symbolic architectures, can be integrated to add more reasoning capabilities. So let's dive right into it. So in this talk, I encourage you to ask me questions. And if you have any doubts or if there's anything unclear, you can always interrupt me and ask. Further to that, we can also have a Q&A session at the end if you have more questions. All right, so the agenda for our session will look at some motivation on why we actually need to see what's going under the hood in an LLM. And let's look at few definitions and go into the internals, the transformer architecture and the embedding spaces, and a bit about how large language models trained and inference in practical scenarios. All right. So this is a small activity that I wanted you to try out as well. So this is a small brain teaser. So Nick's grandmother has 4 kids. One named North, another called South, and one East. What is the last child's name? So any answers? So Nick's grandmother, that means, let's think Nick is me. My grandmother has 4 kids. That's my mother and few more my mother's siblings. So one named North, another named South, and one named East. So what is the last child's name? So what do you think of the answer? Is there an answer here or any answers? Nick, all right. Michelle says Nick. So is it Nick? So Nick means Nick is not the 4th child, right? There's no answer here, right? Nick's grandmother has 4 kids. So Nick's mother has 4 kids. So let's try and ask this question on ChatGPT and see what it will do. So I have copied the chat. So this is the ChatGPT. I'm sure you are pretty familiar with this. So I will use the reasoning model. So Nick's grandmother has 4 kids, one named North, another called South, and East. What is the last child's name? So technically there's no answer, right? So Nick is not the answer because Nick is basically the grandson. So let's see. It says solve in the riddle. It'll try to reason a little bit longer. So it says answer is Nick, right? So you can see like, so although we see that in benchmarks, most of these reasoning models do really well. At the end, a simple reasoning question like this, ChatGPT or any other reasoning model can't do. So one take-home activity that you can do is, if you have access to DeepSeek, you can ask this question. I will post it on the chat as well. DeepSeek solves it in a different way, which is very interesting as well. So you can see, like, simple reasoning questions like this, ChatGPT, even the reasoning models fail. So we can try one more using the general 4O, that is not a reasoning model. So let's see. Yeah, so again, the last child's name is Nick. So what's going on? So if we go back to the reasoning model and ask the question again, so I'll bring up the chat. So we can look at how it reasoned. The riddle asks about Nick's grandmother, who has 4 kids. The names given are north, south, and east. So it says, so it tries to give some answer and picks Nick. So you can see, like, it's weird, right? Although it can perform really complex mathematical tasks, even for a simple reasoning problem like this, it fails. Another motivation that we can look at to understand LLMs a bit deeper is this paper called Lost in the Middle. So it basically, it was the first time that the reasoning in large language models, it was revealed that whenever you have a large text that is fed into a large language model, the information in the middle is actually kind of lost. So this is sort of the demonstration in the paper. So let's say we give a large text and we ask a question where the answer is in the middle of the large text. So if that is the case, so this is the position of the document. So if that is the case, if it is in the middle of the document, we notice that there's a significant reduction in the retrieval. So this is same for large context. So it especially happens when the context is large. So this x-axis is the context length. Context length means the number of words in your prompt. And this is the percentage of the answer placement. So in here, you can see this is for GPT-4. So you can see at a certain around 64K, after 64K, it starts to perform really bad. So sometimes even 0%. So again, a weird thing to happen, right? When you pass in a certain question, information in the middle is lost. And if we ask a simple reasoning question, it fails, but it can solve much more complex ones. So let's try to understand a little bit about how large language models work in terms of the internals. So that is the main motivation for today's talk. I hope this will help you in your algorithmic design as well. All right, so the formal definition from IBM is something like this. Large language models are a category of foundation models trained on immense amounts of data, making them capable of understanding and generating natural language and other types of content. So there are like few popular large language models. Of course, the ChatGPT was the most famous, and Gemini and Claude and Meta AI, and also Perplexity. So these are some of the most famous large language models. So you can try the question that I posted in all of these, and they try to solve it in different ways, which is also very interesting. So how do we understand large language models? So the first thing that you can think of a large language model is you can imagine a library. Imagine a library that has many books and vast range of books in different topics that covers almost everything, every knowledge in the internet. And think of the librarian in that library. So that librarian has read every book, right? And large language model is something like that. Large language model is like that librarian. So there are a few things that you have to keep in mind. So although a librarian has read that whole library, when we ask a question from the librarian, that librarian cannot will not go and pick the book and read it again and give you the answer. It will, the librarian will just give you the answer depending on the memory he or she has. So basically, that means that librarian has more of a compressed knowledge of this large collection of books. So there's a chance that it might get it wrong. Whenever the question is asked, there's a chance that it might get the answer wrong. So you have to think of these large language models like ChatGPT, DeepSeek, Gemini as probabilistic models that can get most of the questions correct, but sometimes get it wrong. So here's another question for you. So we use computers in our day-to-day lives too. What could be the next word? So I want some answers for this in the chat. Maybe if you can speak up, that's also encouraged. We use computers in our day-to-day lives to what could be the next word? We use computers in our day-to-day lives to work. Yes, great. So work is a good one. I will give another one. Maybe help. We use computers in our day-to-day lives to help our work. Maybe. So you can see if there's any more answers in the chat. No, I see work, study. Yes. So yes, we use computers in our day-to-day lives to study. That's also true. So you can see the next word. Three of us came with different answers. So this is the same way that large language models also work. So it's more like the next word prediction models. So if you give this to a large language model, what it will do is it will come up with the next word based on the training data it has seen. So it has already seen lots of scenarios and come up with a probability distribution. So basically, do has the highest probability in this, according to this sentence. Do, help, perform, communicate, make, accomplish. You can see these are like different, has different probabilities. And it will randomly pick one of these to randomize the answer. So that is why whenever you ask the same question from ChatGPT at different times, it will generate different answers. So there are parameters that you can tune, but that's a different topic, which is not focused today. All right. So this is, so I wanted to mention is like, this is how large language models work. So it is basically a next word prediction model. So the summary is large language models are basically next word prediction models. So if we look at the internal structure of a large language model, it has few blocks. I will come to that later. But what internally happens is whenever we pass in a text, like we use computers in our day-to-day lives too, it will pass in this text to the large language model. It will do some transformations, and it will come up with the next word, which is do. And in order to keep this generation going, what it does is it will just feed the same, this generated text we use computers in our day-to-day lives to do back into the large language model so that it will continue generating text for that sentence. So these are what we call autoregressive models. It will sequentially do it. That's why you usually get sequential answers whenever you ask something from a large language model like ChatGPT. All right, so hope that is so far clear. And so let's see what actually internally what happens in large language models. So the basic idea here is there are a few things that you have to understand. So the first thing is this transformer block. So transformer block I will talk about the token encoder first. So token encoder is the first block that the text will see, and it will be the one which convert these natural language to some sort of numerical representation and pass it on to this transformer block. So transformer block is the high level idea here is transformer blocks will understand patterns in the text, which we'll talk in a bit, and it will be passed to an neural network or multi-layer perceptron, and that is where the next word prediction notion comes in. So transformer block is more like learning the words, learning the structure of the sentence, and the neural network is basically kind of like the next word prediction. So this is based on the initial large language model that was popularized, the GPT-3 from OpenAI. So this is a basic structure. So in each of these transformer blocks, we have something called attention heads, which we will look at in a bit. So attention heads will focus on different patterns. So you will see it in a bit. And finally, what we do is, once these numerical transformations are done, we have the token decoder, basically the reverse of this token encoder, to generate the next word. All right. So the first thing that you need to understand is this notion of word embeddings. So let's say, so we have some text like this. We use computers in our day-to-day lives. So the idea of word embeddings is it will preserve the word semantic relationships between words. So for example, if we have in this space a position relevant for king, and if you have a representation for the queen in this embedding space, so let's say the distance from king to queen is towards this direction. Similarly, for two words like man and woman, this direction will have that gender like direction. So these embedding spaces are sort of like works before the large language models. This has been around for maybe more than about 10 years now. Word embeddings has been there for quite a bit of time. So the idea of word embedding is understand the meaning of words in this. So this, like in this example, it's like 3D space, but it's more like very high dimensional. The idea is to understand the word or the notion of certain concepts like gender, or the verb tense, or past tense, or the country capital. So in different directions in this embedding space. So hope that made sense. So to summarize, so embedding model will basically have certain directions representing certain meanings. And then we come to, so the next concept is attention. So I will put these all in together. So we'll just first look at one by one. So attention is the mechanism in the attention heads, which will learn the context of each of the words. For example, so let's say the ring sparkled brightly, right? Another sentence, if you look at, they ring the bell. And another sentence would be, she joined the ring. So in each of these sentences, the word ring will have a certain embedding that is fixed, right? So embedding means the position in this vector space. So each of these ring word will have the single embedding, which is relevant, which is a position in that embedding space. However, the meaning is different, right? So in the first sentence, it is a ring like this that you wear in your hand, and In this case, ring the bell means it's a doorbell. And in this case, it's a circle. So the idea here is in attention mechanism, you can give some context to this word ring or change this embedding slightly so that it will give the meaning of this actual meaning of the sentence into this ring word. All right. So let's look at an example and let's try to bring everything together. So let's look at this example. The cheerful, chubby student then began a PhD, right? So this presentation was originally presented for PhD students. So the cheerful, chubby student then began a PhD. So let's, for simplicity, let's look at this word only, the word student, right? So a typical student would look something like this, but it must be slightly changed, right? So let's say this is the embedding space, the position of the embedding space, embedding word student. So this is the place. So this has to be slightly changed to cheerful, chubby student, right? So it could be something like this. So the idea here is we need some sort of mechanism to alter this original embedding location of the student to this cheerful, chubby notion plus the student, right? So that is the main idea that we will look. And this is where the attention mechanism helps us in this case. So the first thing in large language models, what it will do is, will basically have each of these words some vector representation or embedding. So this is like fixed for each of the words. So you can think of this as tokens, but for simplicity, let's look at this as words. So different words have different embeddings. Embeddings means these vectors. So initially what it will do is it will basically position encode, or that means this word appears first, second, third, fourth, and fifth. And these embeddings, initial embeddings will be position encoded, and basically now we will have 8 vectors that is position encoded for each of these words in our given sentence. Let's call them E1, E2, E3, and up to E8. All right. So let's look at what happens in one of the attention heads, right? So we learned that about transformer block, and transformer block has multiple attention heads. So first we will look at one attention head and try to understand what it will do. Then focus on other attention heads and how everything will come together. So here, this attention head, let's assume this attention head answers this question. Are there any adjectives before me? This attention head specifically answers this question, right? Are there any adjectives before me? So in this case, there are 2, right? Cheerful, chubby. So this attention head will basically answer this question. Are there any adjectives before me? And yes, there are. So the goal of this attention head is to somehow identify these 2 words. All right. So this question, are there any adjectives before me? So this question is embedded into what we call a query vector, right? So this query vector is the one that represents this notion of, are there any adjectives before me? And we basically, so this query vector is something that can be generated for each of the embeddings using this query matrix. So query matrix is a learnable matrix in large language models that is learned during training. So the notion of this matrix is basically that, are there any adjectives before each of the words? So in our special case, we will only think about students so that it will ease our understanding. So we will get the question like, are there any adjectives before the? Are there any adjectives before cheerful? Are there any adjectives before chubby? Are there any adjectives before student? So these vectors represent that notion of adjectives before me. So in order to get the answers, we, in attention mechanism, what happens is we also have something called this key metrics, which will provide the answer to the specific question asked by this query metrics. So we have the same embeddings, so 8 embeddings. So initially we have 8 tokens, it converted to 8 embeddings. So again, we have the 8 embeddings on this side. Basically, we multiply this by the key metrics, which is trained again using during training time to answer this question. So in this case, cheerful and chubby, the embeddings for cheerful and chubby will give the K2 and K3 vectors. So we have something like this. So I'll go back. So the idea here is these metrics, WK and WQ, those two are trained so that for this specific question, are there any adjectives before me? This query and the key metrics, the generation, after you sort of pass these embeddings through this key metrics, these resulting vectors will have similar or high dot products or similar in vectors. So the idea here is like, in order to give the answer for this query, these cheerful and chubby will have similar type of vectors, similar in which has less cosine distance. So it will have high number of, so technically what it will do is it will basically calculate the dot product between each of these query vectors and the key vectors. So if they are very similar, it will have a higher dot product in this sort of n by n squared attention pattern. We call this the attention pattern. Basically, the query and the key, the dot product between the queries and the key vectors. Any questions so far on this? So the idea here is you basically answer the questions using the key metrics, and you ask the question from the query metrics, and basically you get the dot product. So if the dot product is high, that means this embedding or the student has some connection to this cheerful and chubby in this specific attention head. All right, we have one question on the chat. Answer that. When giving tokens to words, do we have to consider relationship between the words around them, or later we place those tokens in embedding space around to their relation through training? Yes, great question, Prasan. So how it works is tokens, when we give the token a vector, it is a fixed vector. We do not alter it at the initial stage. It is only in that transformer blocks or the attention heads that embeddings will be changed based on the surrounding words. So initially, when you choose the embedding vector, that is a fixed vector for each word. So it's like a dictionary. So when you get the word student, you just you refer the dictionary and give back the embedding vector. Hope that answered the question. All right, so we are here where we generated the attention map. So we call this the attention map. Basically, you will have higher values for the correspond or related words. So student, cheerful, chubby. So in this attention head, we are specifically looking at only the adjectives of a certain word. So next what we do is, in this attention blocks or this attention head, what it will do is it will do a something called masking, just to prevent that the model will not learn from the future words. So this word has to have connections with prior words, right? It can't have connections in the future words. So in order to prevent that, we basically remove this section. We call this masking. So this is where the complexity in large language models occur, because you have to have n squared. That means the size of the context window. So in this case, 8. So if the input is 8, you basically have to compute a matrix of about 64 in order to get the attention pattern. So that is why initial large language models only had about a very limited context window, about 4096, and later GPT-4 came with 32,000, and now it's about 100,000. So there are different techniques on how you reduce this size, which is again out of the scope of today's session. So now we have a grid of sort of like values that has identified the meaning or the adjectives of each of the words. So we no longer need this Q1 and or the query embeddings or the key vectors. We will remove them. All right, so now we have something like this. So the initial embedding location of student is somewhere here. And we have already identified that cheerful and chubby are two words that will affect this keyword student. Now our goal is to basically change this embedding E4 so that it will have this cheerful and chubby notions. How we can do that is basically we can use these as weights and basically sum them up to give this notion of cheerful and chubby. So there's another concept called value metrics. So I think so the main idea of this value metrics is how much change should I give to this word student in order to make it cheerful, chubby. So it's basically it has the notion of giving the required change in order to alter this original embedding student so that it will have the cheerful and chubby notions. So then what we do is basically, based on the attention pattern, we weight these changes and get a sum of changes that has to be done to this student embedding. So initially we have students. Now we have sort of like this delta E4, which shows this cheerful and chubby idea, and you basically add it to get the resulting vector. So in here, you don't actually add it, but you can think of it as adding. So any questions on this? Any questions on this attention head? So that's the most hardest part in understanding large language models. So understanding the attention head. So if you have understood this, you're good. Any questions on this? On the chat. All right. If there's no questions, I will move forward. All right. All right. So this was only one attention head, right? So we looked at only one attention head that questioned, are there any adjectives before me? So there are more attention heads. In GPT-3, we have about 96 attention heads that has different questions asked. So these are like not more trivial questions like this. These are like a bit more harder to understand what each of the attention heads answer or question. But you can think of something like this. One attention head might be for adjectives. One attention head might be what were the words before 3 words to be. So likewise, the different attention heads will have different questions asked so that it will learn from all the text surrounding each of the words. And once you have all these attention heads, outputs of these attention heads, you basically sum them up to get the final learned representation in this one transformer block, which has some notion of the surrounding words. Does that make sense? All right. All right. So after that, what it will do is, so going back, we initially input the embeddings, the original embeddings, and we pass it through a transformer block. So these attention heads will run parallelly on these embeddings, 8 embeddings, and it will result some sort of learned embeddings that have the context of words surrounding it. And so where does this next word prediction come? So for example, let's say we give a sentence that has the word Michael Jordan, so who's a famous basketball player. And so the knowledge of like Michael Jordan plays basketball is stored in this neural network. So neural network is has the most parameters in a NLP in these large language models. I think it's about 2/3 of the parameters in the initial GPT model was in this neural networks. So here, this is where the actual information is stored. So basically, the transformer blocks learn the context around the words, and the neural network will give the notion of the next word prediction. All right, so that's about the internals. So basically, you will have transformer block, then a neural network, then again a transformer block, then again a neural network. Likewise, in GPT-3 initial model, there were about 96 transformer blocks. And finally, it will have a series of embeddings, which will be decoded back to generate this final word. All right. Any questions? So this is about it actually. So next, we will talk a little bit about how these are trained. So yes, if you have any questions, chat. All right. So did we answer the question? Like initially, we saw that there are simple reasoning question was not able to be solved, right? Like from ChatGPT. So that is why the prompting matters. So I go back. So in this attention pattern, what happens is it will try to change these embeddings based on previous words, right? So if your prompt or if your text is not really descriptive, then these changes that attention heads will add to each of these words has less meaning. So that is why prompting works. So whenever you prompt with a good structure and good meaningful or related content, that is where these models will identify the change it needs to be done to each of the words and find its final position, this cheerful, chubby student, in the right location. So if you give some garbage before with your prompt, this location will be slightly changed, thus generating a different results. All right. All right, so let's quickly look at how training is done on LLMs. So the initial phase of training any large language model is this concept of pre-training. So pre-training means you basically take basically a good portion of the internet in text data and basically feed it into a large language model that we just discussed embedding model, then the transformer block, then the neural network again and again, and hoping that it will train or understand the language context, language structure. And so with most of the models, after I think about more than about 500 million parameters, these pre-training will start to understand really good in a good level. So this is where the most computation resources are required. And that is why most of these large language models are just limited to giants like Microsoft, Google, and OpenAI, because this requires a very large amount of capital. So I think for training, pre-training a large language model is done maybe about twice a year in an organization, even in OpenAI. So you can think of the cost that involves. So pre-training is the most hardest part, which basically takes a large bunch of text data from the internet and basically feed it into the large language model, and it will train and understand the language structure. Then we go to a stage called supervised fine-tuning, or SFT. So this is where you curate the large language model using handcrafted data sets, which are in high quality. So this is where the pre-trained model learn how to behave as helpful assistants. So it will make the behavior more safer and more conversational, and also following better instruction following. You might have seen that models have like 7 billion instruct. So these instruct models are specially tuned to be more instruction following settings using SFT. Then comes the reinforcement learning with human feedback, RLHF, which was the breakthrough technology that GPT was able to release their models with high generation accuracy. So here, how RLHF work is, so basically you have the first pre-trained model, that is the model that you get out from training on the internet data, and you train on the hand-curated data set, the supervised model, SFT, using SFT. And this pre-trained model is a reward model. So here what we do is we use a reinforcement learning technique to basically come up with some sort of reward. So how it does is, so again, we have a subset of samples from the data set that we had for SFT, and pass it on to this pre-trained LLM, saying, all right, so this is a better answer than this. Let's say, for example, one of these samples is to generate a poem on, let's say, computers. So a human can evaluate, all right, this is a better poem than this. So you give that feedback to this pre-trained LLM, and basically it will learn using a reinforcement learning algorithm to penalize negative samples and incentivize positive samples. So finally, you don't want human intervention every time once you have this reward model trained. So once you have the reward model, you will basically train this supervised LLM using this reward model, just like a human, to better align with the goal that it should achieve, maybe an instruction following or a conversational agent. All right, so that's about training. So pre-training costs the most. SFT and RLHF are less costly. So these are like things they do monthly, but pre-training is something that they do once or twice a year. All right, so a bit about inferencing on how they implement these large language models on. So one trade-off that these large language models has is the model size. So like the GPT 3.5 initial model had about 175 billion parameters, and GPT 4 they OpenAI didn't publicly disclose, but it's suspected that it's about 1 trillion parameters. So you can think these parameters. So it is like a general understanding in the industry that larger the model, better the performance. So still, there's no sort of like a bottleneck seem to be. So if you have more power to train larger model, that's a high probability of success. So one method of bringing down the size of these models is through this idea of quantization. So quantization has been there for a long time, and quantization basically means so the parameters in large language model, or weights we call it, will look like something like this. Basically, you round it off to a certain degree. So just to save some bits. So this will affect largely on the capacity or the weight of the model. So you might have seen large language models. There are like 70 billion ones, and you will also see like 7 billion parameter models. So that is how these are generated. Quantization is one method. The other one is the distillation. So distillation means you basically train a larger language model, let's say a 70 billion model, and you ask it to generate text. And on that text, you train a much more smaller or a student model. So this is what we call a distillation technique. You have a larger model and you train a smaller model. So there are rumors like GPT-4o is a student model. So OpenAI also has much larger model. So that's just a rumor. So yes. So this is about a bit of inferencing. All right. So that's about it. So any questions? And thank you for joining and as well staying till the end. So if you have any questions, I'm happy to answer. Any question? All right. Have 10 minutes for questions. So,
All right.
all right.
Seems we don't have any other questions, so let's. It's time to wrap up the today's session. So let me thank our speaker for today, Vidura Sumanasena, for delivering an insightful webinar. And our next webinar is scheduled to 28th of March. So that's next week. We have a change in topic there, but we will let you know through the social media and through emails. So I thank everyone who attended today and have a good night.
Thanks, everyone, for joining.